Hello, my name is Matthew and I'm with the Tampa Hillsborough County Public Library. We welcome you to Planet Hunting with TESS's Natalia Guerrero. This is part of our New Gear, New You month. We're doing all kinds of things related to science and technology. We've got actually another event coming up with Natalia on the 27th at 6:30 p.m. So be sure to check that out and register if you have not already. And we have things like tech topics happening on a weekly basis and tech rescue if you need a little one-on-one assistance with whatever technology related issue that you're dealing with. But that's what the month is all about. We wanted to start the year out in waving our nerd flag. So I hope you'll join us with that. And also, before we begin, we want to do our book shout out. This is actually a book series shout out that was recommended by our guest tonight. And it is Ada Lace. You can see it's actually a series of 5 books that you can check out through the library and find out about how she uses her love of science and gadgets to help solve problems with her best friend Nina. It's a really cool chapter book series for upper elementary, and you can go to hcplc.org/books to find out more about that. So now, without further ado, I'm really thrilled to welcome Natalia Guerrero, who comes to us from the Massachusetts Institute of Technology, and her work with the NASA project TESS. I'm going to let her tell you all about herself and the project and some other cool things.
All right. Hi, everyone. My name is Natalia Guerrero, and I am a physicist by training. I went to MIT in Boston, and I now work for MIT on the NASA TESS mission, which launched in 2018. That's the middle picture there is me standing in front of the Falcon 9 rocket at Cape Canaveral just a couple of days before TESS launched. I am also a science communicator. I love talking to people about my research and the research my team does. But I'm also interested in the arts and in how science and the arts can connect. And actually, for 3 years, while I've been working at MIT, I've been a radio DJ at MIT's radio station, WMBR, playing all sorts of different kind of vocal and electronic music and trying to connect those two parts of my interests. So I have been an astronomer working with TESS for the last 5 years. And a lot of what astronomy is asking lots of questions. And so in my research recently, I've been asking a couple of questions. The first is, how unique is Earth? We know that there's no place like Earth in our solar system. We're the only planet with liquid water. We're the only planet with land and ocean, with an atmosphere that we can breathe, with clouds in that atmosphere, and with a magnetic field that protects us from the radiation from the sun. This is a really special place, and I'm very glad that we live here. So, but this question leads us to another question, which is, if the Earth is unique in the solar system, is Earth unique in the galaxy? And that leads us to another question of, are we alone? And are we alone as a planet that looks like ours, but also are we alone in terms of life? The search for life is just now getting started as the field of exoplanets has exploded. And so this type of asking a series of questions is really characteristic of how a scientist thinks. Coming up with a new question, looking at what we already know, learning from that, and then if needed, collecting new data, investigating new things, and then feeding that data back into more learning, more questions. So my research focuses on exoplanets, or planets outside our solar system. Since we first discovered proof of exoplanets 30 years ago, this field has exploded, and we now know about thousands of exoplanets. And with new telescopes like TESS, we're learning about even more. So we don't actually get to take pictures of exoplanets for the most part. Stars are really bright, and so it's hard to capture that image of an exoplanet. But what we can do is measure the starlight and see how it changes as a planet crosses or transits in front of its host star. So a large planet will make a large dip in the starlight we measure, while a small planet will make a small dip. If there are multiple planets orbiting a star, like in our solar system, you'll see multiple dips coming from each of those planets. I like to liken this to the sibling crossing in front of the TV. They're transiting and blocking out the light from the TV, which is what you really want to see. So I'll go to my next slide. So this is what this actually looks like in reality. You have small amounts of variability in the star's light, and then as the planet, that tiny black dot, crosses in front of its host star, it makes a tiny dip, and then the light goes back to its original level. So the transit, as we graph this over time, creates a light curve, this change in brightness over time of the starlight we measure. So TESS is a spacecraft that was launched back in 2018 that uses 4 wide field cameras that are very sensitive, that they can measure these changes in light that are less than 1% a lot of the time. So this would be like trying to detect a moth flying in front of a car headlight. TESS could detect that. That's how sensitive these cameras are. So I was on the testing team for these 4 cameras, and it was really exciting to get to work on something that was eventually going to go to space. And so TESS launched in 2018. This is an illustration of what the TESS orbits looks like. So it takes about 13 days, 14 days to orbit the Earth in this elliptical orbit. In the blue part of the orbit, that's when it's staring out at one spot in the sky, taking data, and then it turns around during that orange segment and downloads all of the data back to Earth. And it does this over and over again, and it's been doing that for the last 2.5 years. The gray line that you see in this animation is the moon. The moon interacts with TESS gravitationally, and its tug keeps TESS stable. So TESS looks at one spot in the sky, one long strip called a sector, for 2 orbits or about 27 days, almost a month. TESS carefully stares and then steps to the next sector every month. And so over the course of 2 years, we imaged first the southern half or hemisphere of the sky, and then the northern hemisphere. The parts at the top and bottom where each sector overlap get almost a full year of observation, which is really exciting because it means that we get a movie of almost the entire, a movie that's almost a year long of that part of the sky. So these are what the TESS images actually look like. They're these huge wide field images that overlap and give us this beautiful map of the entire sky. There's a chunk missing, and that's because TESS avoided a part of the sky where scattered light from the Earth and Moon would make it too bright to see any changes in starlight from planets. So TESS has found thousands of exoplanets in its own right, and that's what my team at MIT does, is we search in the changes in starlight from these millions of stars and find planets and signals of planets, and we put them together into this catalog. And so the magenta dots are planets that we found in the first 2 years of the TESS mission. And TESS is now looking again at the bottom half or the southern hemisphere. And that's what those blue dots are. Those are new planets that we've discovered by looking again at that part of the sky. So this is really exciting for me to contribute to this major catalog of exoplanet candidates that astronomers all over the world can now look at and better understand what are exoplanets. So now it's time to analyze some TESS data. So if we zoom in on those big wide field images that I showed before to a single star, this is what it looks like, a little blob of these square pixels. And you may notice that this image looks like it's in black and white, and that's because it is. All TESS is doing is measuring the amount of light. No information about the color gets saved. So we apply color when we look at these images on the computer. We say, okay, where there's no light, I'll make that black, and where there's a lot of light, I'll make that white, and then I'll scale my pixels that way. So let's go to the next slide. And so we measure the change in starlight over time. We draw a box around the pixels that we want to count up, and we make a graph of brightness over time. And we can see visually that there are some dips in this light curve and that they're spaced apart evenly. meaning that they are happening periodically. This is something is causing the light to decrease that we measure periodically. So yes, now play that sound sample so we can also hear this. The next question we ask is this an exoplanet? And if we go to the next slide.
So this is our first poll, everybody. Get ready to vote based on the sound that you just heard.
All right, so we're a little undecided. So some yeses, some maybes, a few no's. So let's go and see what this candidate actually is. This is an exoplanet. This is a planet that was discovered by the Kepler Space Telescope. It's Kepler 12b. And the reason we know this is because this pattern is periodic. It's happening regularly, just like the orbit of a planet happens regularly. And it is shaped in a way that tells us, okay, this is something small crossing in front of its host star. So I'll tell you a little bit about this planet, what we know about it. This periodic transit is happening every 4 days. That means if you lived on Kepler 12b, your birthday would be every 4 days. This planet is about twice the size of Jupiter, but it's only half as massive. So it weighs half as much as Jupiter. And this is what we call a hot Jupiter. Our planet Jupiter is really far away from the sun. It's cool, but this planet is twice as big as Jupiter, but only 4 days away from its host star. It is this really unique system of planets that we knew nothing about until we started looking for them. All right, so let's go to the next one. Is this an exoplanet? So let's hear the sound sample. We can already see it's wavy. There's a little flare. So let's also hear what's going on. All right. So I don't know if you heard that high-pitched tone, but that was that little flare that you see where the x-axis says 1746. I think that's really cool that you can hear the flare. All right, so let's ask everyone, is this an exoplanet? What do you think? Also, this kind of simulates the process that I go through with my team every single week when we're looking at new candidates. We look at them together and say, okay, does this look like an exoplanet based on what we know? And we do that for hundreds of candidates. And that's how we get our catalog of targets for other folks to go look at. All right, so got some no's, got some possiblies, and got some yeses. All right, so let's see, Matthew, what this candidate is. So if you guessed no, or if you had a hunch this was no, you were right. This is actually stellar variability. Stars have their own thing going on. They can get bright, they can get dim, they can have these sudden flares. Our own sun is fairly quiet, so we're really lucky. But some stars have these really active behavior. And so this light curve is capturing that variability. All right, so we have one last candidate to go through together. So let's take a look at that. All right, based on what we've learned in this crash course on searching for exoplanets, do you think this is an exoplanet? We see again, the dips are periodic. There's a little bit of noise. Let's hear what it sounds like too. All right. What do you think, everyone? Let's do a poll. Yes, no, or I have no earthly idea. I love that. All right, so I have a lot of confident people here, a lot of folks who think that this is, yes, an exoplanet, couple of no's, and a couple I have no earthly idea. I am here for that. All right, let's see what this was. If you guessed yes, you were right. This is an exoplanet. This was actually a planet that was observed before TESS began, and TESS re-observed it. So we gave it our own name, TESS Object of Interest, or TOI 432b, but it's also known as WASP 35b. And if we go to the next slide, we can see an artist's illustration of what this planet might look like. So this is another Jupiter, hot Jupiter-like planet. Here it is compared to the size of Earth. So Earth is teeny tiny compared to it because it's about the size of Jupiter. It's about the temperature, and it's about twice the temperature of Mercury. I mentioned before that hot Jupiters orbit their stars in these really close orbits. This orbit is 3 days. The orbit of Mercury is 37 or 87 days. So this is way closer to its host star than even Mercury. And this planet is also about the size of Jupiter. So this is how we have used data and asking more questions and analyzing this data to help us understand that no, we're not alone in the universe. There are thousands of exoplanet siblings for our Earth. And Earth is a very unique planet, but there's all of these other really interesting planets out there. So I will pose this question to you again. Let's go to the next slide. What are you curious about? You can use this process for yourself of asking a question about something you want to know about, learning about it, seeing what you already know, and then getting more information about it, taking data. So I would invite you to reflect on this. And in this new year, think about something that you want to learn more about, that you're curious about.
So, okay, thank you very much. Just as a reminder, everybody, the questions section is where you can put in your questions and also responses to the question that Natalia just posed. What are you curious about, in life or in school? We definitely want to hear from you, and we'll be sharing at least some of your responses as well as some of your questions. And I think the initial question we want to start with here, one second, is, okay, oh, do you get to name the exoplanets? Yeah, that's a good question.
Yeah, so I wish we got to name the exoplanets. I actually have another slide, the next slide,
Oh,
talking about this. So I talked a little bit before about how we name the planets. We give it sort of a handle of where it comes from. Ours are called TESS Objects of Interest. And then we have a number for the star that it orbits. So this is kind of like your last name or your family name. So this one was star 423 for us. And then we give planets letter names specifically. The star is A, and then planets go B, C, D, E. And so Earth would be Sol C in that system. So if we go to the next slide, this is also a handout, I believe. You can come up with your own name for your own imaginary exoplanet. Or if you were an exoplanet, what would your name be? This gives you a little
yes.
rubric for
Oh,
that.
I'm just going to reinforce that. Yes, Natalia, we have a couple of handouts in the handouts section, and this is one of them. So you can click on those actually now. It's best to do it during the session if you can. If you don't end up getting that to work, you can get in contact with the library. We'll have some contact information at the end. But you can click on them now. It may navigate you away from the session, but then you can kind of come right back to us. We'll be on for at least another 5 minutes or so, maybe longer. So yeah, be sure to click on those and you can participate in the activity. It's a really good one. Just another question here, which is about, how can people learn more?
Yeah,
And
so if
actually,
you
that's on that next slide deals with that too. I think so.
Yeah, that's perfect. So
Okay.
there's a lot of different resources online for that. And there's actually a website where we put all of the test data and you can look for transits yourself. So that's planethunters.org. And real exoplanet discoveries, real academic papers, including an 83-day planet, have come out of this website. So if you really want to go check this out for yourself, I highly recommend it.
Great. Well, we do have some questions coming in. So I'm actually going to turn off the screen sharing and we can get to some of those questions. One of them, oh, why did the sound stop for a moment in TOI 432B? First of all, I want to commend you, one of our young viewers, for citing the specific, the specific TOI number. But was that a streaming issue, Natalia, or was that actually part of the capture?
What you picked up was a real artifact of the data. So I remember that animation I showed of TESS going around in its orbit. So TESS does 2 orbits per observation sector. So in the middle between orbits, there's a gap where it downloads the data from the first orbit, and then gets the commands for doing the second orbit. So what you heard was that gap where there's a download period.
Great question. Okay, there's the next one. What about wandering planets? How are those analyzed?
Wandering planets.
I don't know. I'm not familiar with wandering planets.
There is a type of planet called a rogue planet, and those are
Oh,
planets that we think have been ejected or kicked out of their solar system. And so there's a couple of different sneaky ways of detecting those. And one of them is, as the planet is sort of floating through space, it will sort of pass in front of stars that are in the background for that planet. There's always going to be a star in the background. And so you can measure that occultation, or that blocking of that star's light, and say, hey, I think there's a rogue planet here. And so there's different ways of measuring that, whether it's the light getting blocked or bended by a rogue planet, that you can discover it.
very interesting. We have a comment here. I like your presentation, so that's great. Awesome. We're glad you guys are getting a lot out of this. Another question here, is your job hard? That's a good one, because I can remember really liking science, but there were certain science classes and in tech too that I had a difficult time with. Geology, like I loved geology, but for some reason I had a hard time retaining all that information. So yeah, what about it, Natalia? How hard is your job?
I love a challenge, so I think that may be why I ended up in this field. But actually, the hardest part of my job is that we're all over the world, and we're in different time zones, and we have a lot of different experiences. So working as a team is often the hardest part of my job. And the science, once you sort of get your head around it, you can always ask someone for help to help you explain it, to better understand it, to learn something new. But getting people to work as a team and all have the same goal, I think that's one of the most fun parts, is when you can all sort of come together and get really excited about science.
Absolutely. Here's a question. How long it says does it take, but I think maybe did it take to find the first exoplanet when the mission began?
So TESS launched in April of 2018, and then we started taking real data in July of that year. And then a month later, the first set of data came down, and we sat down at the computer and just analyzed it as quickly as we could, just to look for something new. And so actually, one of my colleagues, Chelsea Huang, knew that there was a system that had a planet with 1,000-day period around it that we weren't going to measure. But it was a really bright star. And so she said, okay, I'm going to just analyze this one as a sample. And she found a short period planet around that star. It was called Pi Mensa C. And that was in our first couple of weeks of analyzing the data from the first sector of TESS data. So it was a really quick process.
That's amazing. Okay, well, I don't understand this question, but I'm going to ask it and see if you understand it, okay? Is Earth in Goldilocks zone?
That is a great question, and something I didn't mention, but the Goldilocks zone means that it's not too hot or too cold, something we also call the habitable zone. So definitely, yes, Earth is in our Goldilocks zone, because we can have liquid water on the surface of Earth. And when we talk about defining where can life exist? A lot of people define that as somewhere where there's liquid water, because we already know that works. So yes, Earth is in its Goldilocks zone. And so for other exoplanets, we ask, okay, how hot's the star? How far away is the planet? How hot is the star making the planet? What do we think? And so we have already found some habitable zone or Goldilocks zone planets around other stars.
That's really exciting. I mean, it take pretty long to get there, but
Oh yeah.
oh yeah. The trip would not be just right, but the planet is. How many? Oh well, I think you said it early in the presentation. It's 20. Is it 2,400 so far?
Yes, just a little bit
So
over that.
so I think I want to ask a follow-up question to that as well. So has the rate increased as you are going further and further into the mission? Like, is technology improving, or are there limitations that prevent the rate from increasing over time in terms of the number that you find?
We think that we're going to find more planets the more we look, because, like I said about those parts of the data that overlap, and because we're looking at the same parts of the sky again, we're going to have an even longer period of time for which we have this sort of nonstop observation, basically. And so we can find planets that take longer to orbit their star, and so we only get a couple of transits from them, and we've already done that, gotten some long period planets. And we've also had time to make our analysis tools better. So we can now use machine learning, artificial intelligence to pick out planets around fainter stars, planets that have a little bit more of a complex signal, planets that are around a star that's really active. So we've been able to also just like make our programs better. So we're finding even more exoplanets. And so my group actually, we sometimes we decided, okay, we're going to take a bet on how long it takes before we get to 3,000 planets. Like, when this spring is that going to be?
That's a good. It's almost sort of competitive in a way, isn't it?
Yeah.
All right, great. Well, listen, we are running out. We're actually over time. We're gonna just go for a couple more minutes, but while we are getting ready to wrap up and answer just a couple of last questions, I am going to pull my information back up here. Let's see. Here we go. Okay, so I just want to share our contact information with everybody. Oh, hold on. There we go. Contact information for the library. We thank you very much for joining us tonight. You can reach us if you need to at 813-273-3652, or go to that link that is the contact information. Not only can you reach out to us in a few different ways, but we also have the Ask a Librarian service that is very valuable, which you can engage on chat. And we have a lot of great other events coming up. Not just now, we're planning events all the way through the end of the calendar year right now. We've got things that are really interesting for all different ages, and including Natalia Guerrero, who's going to be back with us on the 27th. So please go to hcplc.org/events to find out about that, and the website for TESS, where you can learn more about all the great work that she and her colleagues are doing, is tess.mit.edu. And while I'm looking for these last questions, Natalia, can you remind everybody what TESS stands for?
TESS is the Transiting Exoplanet Survey Satellite.
All right, excellent. So I'm gonna, I think, end with just these last two questions here. One is, of the exoplanets that you and your team have discovered or located, what has been your favorite and why?
I really enjoy, I feel like I get excited about like every new planet. So whichever one's like on the top of the list for latest. But recently there was a planet that we found around a type of star called a white dwarf, which is a star sort of in the last stages of its life before it collapses. It's burned up all of its fuel. And so this planet is much larger than its star, and somehow in the sort of the period of the star's life, the planet didn't get kicked out of orbit. It moved closer and closer in. And so I thought that that was a really interesting system that we found recently.
That is very interesting. And I have to ask, this is like my own question related to that, is do you have any funny nicknames for any of the exoplanets that you've ever found because of peculiar characteristics or anything like that?
I know that some people like to nickname planets after like certain cats, or so if people have cats on the collaboration. We actually nicknamed the test cameras while we were testing them. We named them after different pop culture dragons. So there was Norberta from Harry Potter, Smog from Lord of the Rings, Falcor from Neverending Story. And then Draco, the constellation. So that was our nerdy pop culture link.
Now I have the song stuck in my head. Close your eyes. Okay, so let me stop sharing the screen here so we can say a proper goodbye. And let me ask that last question before we do that, which is there a mission to find extraterrestrial life?
We're getting there. The next telescope to launch from NASA is called the James Webb Space Telescope, and it's going to look at the light from the star as it passes through the atmosphere of a planet, so we can get information about what's in the atmosphere. Is there oxygen? Is there nitrogen, methane? What is there? And that will give us more clues about, is this planet really habitable and what could be living there?
Oh man, that is super exciting. And we are well over time, but it was well worth it. Natalia, thank you so much for joining us tonight. We really appreciate it. And thank you everybody for joining us as well. And please come back on the 27th. It's going to be a whole new presentation and talking about TESS and some other projects. So thank you again, Natalia.
Yeah, thank you for having me.
All right, good night, everybody.
Bye.